Numerical Computation, Chapter 5, Extra Video number 3. You can view this video after you finish the extra video number 2. In this video, we look at finding roots for a special type of functions, that is, polynomials. This is actually an historically important topic in mathematics. Therefore, this is a rather well-studied topic. To set the idea, let's write a polynomial of degree n in the general form, that is, in the powers of x and multiply by coefficients, and we add up. So an ai will be the coefficient for x to the power I, and in order to keep this a polynomial of degree n, we require the coefficient an to be different from 0, while the other coefficient could well be 0. Before we introduce the derivation of the method, let's state a few facts that are well known for roots of polynomials. So first, we are assuming the coefficients ai here to be real number. Then the roots for the polynomial p can be real and complex. In the case of complex roots, if you have a root r as a complex number, that is a root for the polynomial, so is the complex conjugate of the r. About the total number of roots for a polynomial, we know that for a polynomial of degree n, there are exactly n such roots, where the n is obtained by counting multiplicity and counting all the real and complex roots. For polynomials of lower order, there are formulas to compute the exact roots. We are all familiar with the root formula for quadratic polynomials, probably from our study in high school in algebra. Formulas for polynomials of degree 3 and 4 are available, however, they are much more complicated. But they do exist. Now, if you increase the degree of the polynomial to be bigger than 4, then there are no such good news. Albo, a Norwegian mathematician, proved that if n shall be bigger than or equal to 5, then there does not exist an explicit form to compute all the roots. Therefore, in general, one needs to apply a numerical method. Let's begin with locating one real root. In order to find one real root of the problem, one can apply any of the root finding algorithm that we have learned. For example, fixed point iteration, Newton iteration, or secant iteration. We know that for many of these methods, one needs an initial guess, and very often one needs a good initial guess. For example, for Newton's method, we know that the initial guess should be sufficiently close to a root to have convergence. There are some existing theorem or result that one can use to roughly locate an interval that contains the roots, or have a rough idea of how many roots one could expect. The first one is the Descartes' sign rule. It says that capital N, we let it be the number of sign changes of the coefficients ai, and let k be the total number of real roots counting multiplicity. Then k shall be less than or equal to n, and n minus k is an even number. Furthermore, we also have Cauchy's theorem. It's a theorem that gives us a rough estimate on the spectrum radius. So let now gamma to be the maximum of the absolute value of the ratio between the coefficient ak over an. That's the coefficient of the x with the highest power. So you find the maximum of that. Then Cauchy's theorem says that all roots of the polynomial p must be included in the circle of radius 1 plus gamma in the complex plane. So therefore one should start the initial guess within this circle. Assuming now we are successful and have located a real root r for p, then we can use a deflection method to remove this root as follows. The polynomial p, if it has a root r, then it must contain a factor x minus r. Then you can write p as x minus r multiplied by q of x, where the q of x is also a polynomial, but of degree n minus 1, that is 1 less from the p. And furthermore, q of x should contain exactly the same roots as p after removing the r. And then one can iterate this procedure and finding a root for q and deflate it until all the real roots are found. Now let's look at a procedure to compute the evaluation of a polynomial at a given point x. If we start with the standard form of p of x and compute each term, then this computation requires 1/2 times m squared flops of computation time. It would be more convenient to rewrite it in a nested form as follows. So we take out a0, then all the remaining terms would have a factor x, then we take it out, then we have a polynomial, and with a constant term a1. If we take that out, then the remaining one still would have x as a factor, and then we take that out. And we keep going until we reach the last term containing an of x. And this can be evaluated by a for loop, starting the computation internal here and keep going out. And a count shows that this computation requires only 2n minus 1 flops. So here is a pseudocode for that computation, and somewhat similar to the nested form of Newton's divided difference. One start from the inside, we set bn to be the an, and then we compute a for loop, and for k going from n minus 1 down to 0, and then bk will be computed as ak plus bk plus 1 times x, namely the expression in this bracket as we go further and further out. And now it's easy to verify that b0 would equal p at x. So if now x shall be a root, x is r, then one would get b0 equals 0. So here we present a very simple Matlab function which for a given polynomial p and a point z, it would compute the coefficients bk and the value p at z. Note that in Matlab, the indices of the coefficients ak, bk are now with reversed ordering. So the function looks like this. And we call it Hörner, the algorithm is due to him. It takes A, which is a vector containing all the coefficients for the matrix P, and Z is a number. It's at the point where you evaluate the polynomial. And the code will return two values, and B would be the vector, and the vector would store all the coefficients bk, and the v here would be the value of the function polynomial evaluated at the point z. Okay, so it's basically coding the pseudocode we presented in the previous page in Matlab syntax. So n is the length of A, and we initialize by generating a zero vector of length n, and then we set the first one to be a1, which is an in our notations, the coefficient in front of xn. And then we go forward for k equal to n, and we can compute the kth element in b vector to be a of k plus b at k minus 1 times z. And after finishing the for loop, and we extract the value of the polynomial, which will be in bb, in the last entrance of the vector here in bb, and the coefficient for b would be the first m minus 1 in this vector bb. Now, the reason we go through such detail of that computation is that this resembles the synthetic division algorithm, which we have learned in high school. So if x equals r, the procedure one performed to compute the division p of x divided by xr, that is, to rewrite the polynomial p as the product of x minus r times another polynomial. And that is great news, because actually we are interested in the deflated polynomial. And then in that procedure, the coefficients in b here would exactly be the coefficient for the deflated polynomial in this procedure. So here we give this notation q, x, r, meaning this is an expression for the p of x divided by x minus r. Okay, and then we collect them by using just the coefficients b. And then we note the deflated matrix has a power m minus 1. Once it's obtained, one can then repeat the procedure with this matrix and keep going until one has found all the real roots. We can now summarize the algorithm. Given a polynomial Pn of degree n, step 1, find the root Rn for Pn with a suitable approximation method, for example, Newton iteration with a good initial choice. And second, we now compute the deflated polynomial Pn minus 1x. We write it n minus 1 to denote the highest power now. So this is just Pn divided by x minus Rn. And then we repeat the step 1 and 2 as needed. Such an algorithm can be easily coded in Matlab, provided that the function Hörner is already coded, which would compute the deflated polynomial. Combining Newton's method with Hörner's algorithm gives the most used algorithm for polynomial root finding. The great advantage here lies in the fact that one can easily incorporate Hörner's algorithm into Newton's method, as we'll very soon see. To fix the idea, we consider a polynomial Pn, the deflated polynomial Pn minus 1, after removing the root r, such that Pn of x equals x minus r times Pn minus 1 of x. Recall that in Newton's iteration, we need the derivative of the function Pn. Let's differentiate. The derivative of Pn by the product rule equals, differentiating this term gives me 1, then I copy the Pn down here, and then plus keep this term, and I differentiate the Pn minus 1 term. If we set in now x equal r, Pn derivative evaluated at r, then the second term will be 0, and what we have is exactly the deflated polynomial Pn minus 1 evaluated at r. This identity now provides a way to compute the derivatives of Pn utilizing directly the associated polynomial, the deflated one. So here is the algorithm combining Newton and Hörner. Given an initial guess r0 of the root, we compute the following iteration. Rk plus 1 equals Rk minus Pn evaluated Rk over Pn minus 1 at Rk. Now we remark that this iteration works for real roots. For complex roots, one must then work in the complex domain with real and imaginary part. So you have two unknowns, and then the algorithm is much more complex. Although the basic underlying idea could be the same, but the details are more involved. Here is a possible Matlab code for this algorithm, where we assume that the function Hörner is already provided, and we will use it here. So the function, we call it Newton-Hörner, which takes in the a coefficient for the polynomial p in the a, which is a vector, r0, your initial guess. That's a tolerance, and that will be the total number of iterations. And it returns the roots in this vector r and the number of iterations that's being performed in this, and it's here. So some details of this code. So some initializing, one put capital N to be length a minus 1. That will be the power, the order of the polynomial. And then r is a vector of length n, and the number of iterations is a vector of number n, because it stores the number of iterations performed for each root. So it's a vector. And then we go through k from 1 to n to look for each root, assuming they're all real. So ni, number of iterations, set to be 0. X is r0, arrow to be a big number, bigger than tolerance. Then we go into a while loop. Here is just Newton iteration to find that root. Okay, so we call the Hörner, sending a and x. Hörner returns us v, the value evaluated at x, and b, the coefficient for the deflated polynomial. Once we have that, we call the function Hörner one more time, and we send in b as the coefficient, and we evaluate it at x, and we only receive the value here. We put it in dv, and we are not interested in this returned value. And from the discussion on the previous page, we know that this gives us a derivative of the function, which we can use in the Newton's iteration. That is exactly what we did here. The next x is the x minus the function divided by the derivative at that point, exactly the Newton iteration. Then we computed the error to be the absolute value between the values of the two iterations, and we keep count of the number of iterations, and we update the x value. So when this while loop is done, and either error will be smaller than tolerance or the total number of iterations is reached, and then we assume that we have found a root. So one can display an error message in the case where convergence is not reached. So if the total number of iterations equals the maximum number of iterations and the error is bigger than the tolerance, we display a message saying it did not converge. And then we put the x here into the vector r, which stores all the roots we found. So the root number k is stored here. And in this vector number of iterations for this kth root, we store it. And then we call the Hörner function one more time, sending in the coefficient a and sending in the x, which now we know is a root. So we carry out this deflation procedure, and I know it should return a value 0 here, so that's not interesting. So I just neglect that, and I receive the coefficients, and I store it again in this a vector. And then I can repeat and go through the whole process again to find another root and deflate the polynomial one more time. Now let's run some tests. We test the code with a polynomial with double root. So p is just x squared minus 2x plus 1, and we know the two roots here are 1 because this is just x minus 1 squared. So it's a double root. Okay, so here is how you call it. So you write a vector to collect the coefficients, and then you send it in and as an input for Newton-Hörner a, and the initial guess we just put 0. That's a tolerance, e to the negative 15, maximum number of iterations 100. And this is what comes out of the algorithm. It gives you the roots, 1, the first one, and 1, the second one. And it tells you the number of iterations. So for the first root, it went through 28 iterations, and for the second one, 2 iterations. So you might be wondering why to find the first root, the program had to do so many numbers of iterations. So what we did is basically a Newton iteration there. It has quadratic convergence in case of a single root. But unfortunately, when we were locating the first root, it was a double root. And Newton iteration does not perform very well for double roots or for roots with higher multiplicity. Therefore, it's reduced to actually a linear convergence, and it used many more number of iterations. Okay, that's all. Hope you enjoyed it, and thanks for watching. See you next time.